The next other trig function I'm going to go over here involves cosecant. Now, cosecant and secant are related in that we can use as a guide the sine or cosine function as appropriate. And in this case, we're going to use our sine function as a guide. So what I'm going to do is I'm going to come down to the left here and sort of in a different color. I'm going to go through what would happen if I were dealing with the sine version of this function. In other words, I want to use y equals sine of the quantity x over 3 minus pi over 2. What would it look like? Well, this is a graph that definitely has a changed period and a phase shift. Our amplitude on this one is 1, right? So we would go through and we would identify all of these values, recognize that cosecant does not have an amplitude. The period, 2 pi over b, in this case that's 2 pi over 1/3, which is going to give us 6 pi as our cycle. And our key points always occur at 1/4 of the period apart, so 1/4 of the period, 1/4 times 6 pi is going to give me 3 pi over 2. That's how far apart each of the increments of my key points are. And if I'm looking for my phase shift, I'm going to set my argument equal to 0, solve for x. So if I take x over 3 minus pi over 3 and set it equal to 0 and solve for x, x over 3 is equal to pi over 3. That gives me x is equal to pi when I multiply both sides. So this is actually my phase shift right here. So in my table of values, when I make up the one for my cosecant, of course I'm going to graph my x and y values all lined up right here. All of the x and y values that I get for my key points for my sine function are going to be the same as the key points for my cosecant function. So I'm actually okay with that by using x and y right here. X, that means we're going to have a period that starts at pi, and each of our key points are 3 pi over 2 apart. So we're going to be adding increments of 3 pi over 2 to get our key points. Well, pi is 2 pi over 2. So we're going to add 3 pi over 2 to that, and we're going to get 5 pi over 2 as our first key point within that cycle. We add 3 pi over 2 again, that gives us 8 pi over 2, but we know that that one reduces to give us 4 pi. Our next key point is 3 pi over 2 apart from that, so 8 pi over 2 plus 3 pi over 2, that gives me 11 pi over 2. And then my next key point is going to be at 11 pi over 2 plus 3 pi over 2. That gives me 11 pi over 2 plus 3 pi over 2 would be 14 pi over 2, but that reduces to give me 7 pi. And we can check to see that that reflects our period accurately. If we take the end point, the last key point, minus the beginning key point, we should get the period. In this case, we do. 6 pi is our period of this function, so we're doing good. All right. If this were the sine function, the amplitude is 1, and the y values then would go something like this. They would go 0, 1, 0, -1, and 0 at each of these key points. However, it is a cosecant function, and anywhere that sine was equal to 0, that means we're undefined. So this is an asymptote right here. This is an asymptote, and this is an asymptote. However, cosecant of an argument is equal to 1 over the sine of that argument, and so 1 over 1, well, that just gives us y equals 1 at this point, and it gives us y equals -1 at this point. All right, so let's plot what we have. We have this graph that's going to start at pi. We have an increment of 3 pi over 2. So our next key point is 1.5 of the way over right here. So this is at 5 pi over 2. Our next key point is at 4 pi. Our next key point, 1.5 over, that's at 11 pi over 2. It's pi. And then finally our last key point is over here at 7 pi. 1, 2, 3, 4, 5 key points right there. Our vertical asymptotes occur at pi, 4 pi, and it's 7 pi within one cycle of this cosecant function. Our y values, here's 1, here's 1, reducing my 1 and negative 1s here. This is 1, this is negative 1 down here. Y-axis, x-axis. So within one cycle, if we follow along what that sine function does along with its phase shift, we can see at 5 pi over 2, y is equal to 1. At 11 pi over 2, y is equal to negative 1. The graph for the cosecant comes down along its vertical asymptotes, through that key point and back up along the vertical asymptote at 4 pi. Then at 4 pi along the vertical asymptote through its key point at negative 1 at 11 pi over 2. Then back down along its vertical asymptote at 7 pi. So one cycle of our function, cosecant of x over 3 minus pi over 2, is here. One other quick note, we have to be able to determine something about the domain and range of this function. For the domain, we recognize that normally we would be saying the following, that our period would not include values like n times pi, right? We say that if we had a function, we don't want our argument to equal n pi. But in this case, our argument is x over 3 minus pi over 2. So to find our domain, we're going to take the argument x minus 3 minus pi over 2 and set it not equal to n times pi, whole number multiples of pi. We have to solve for x. So by our rules of algebra right here, we add our constant over. So we're going to have x over 3 not equal to n times pi plus pi over 2. Then we multiply both sides of our inequality by 2, and we get x will not equal to 3n times pi plus pi over 2. And so our domain is going to be the set of all values of x such that x is not equal to 3n pi plus pi over 2. Remember, in the basic cosecant model, if we had y equals cosecant of x, we outlined that the domain of that natural function would be the set of all x such that x is not equal to n pi. So that's where I'm basing this value for our domain on. Okay, but wait, there's more. The range. What is the range? Well, the range in this case is essentially unadjusted from what it would be without any change in the value of a. Our range goes from negative infinity to negative 1, including negative 1. That's what happens as we look at the y values here along this axis. Union with the set from 1 to positive infinity. All right, so domain and range, we should be able to get those when it comes to our secant, cosecant, tangent, cotangent functions as well. All right, more to come.